Okay, let's start out with a solved Sudoku. So given those original numbers, here's the solution to the Sudoku puzzle. A 2 by 2 is pretty easy. It takes, 3 minutes to solve as a human being, and we've got a solution. Now, what we're going to do with that solved Sudoku is we're going to prove it to some other person that we have the solution without giving them the solution itself. And they get to ask for pieces of the puzzle. But before we give them back that answer in that piece, what we're going to do is a random substitution. We're going to take each one of our numbers and uniformly pick one of the other numbers to give them as a response. So in our first random substitution, I've got 1 mapped to 4, 4 to 2, 2 to 3, and 3 to 1. Now it turns out that if we do this substitution, that in any one of our little subsections in our Sudoku, we still have a correct answer, as long as each number matches to one of our other numbers in our set. So they can ask for a column, any one of them, a row, any one of them, or any subsection of the Sudoku. So one little chunk up there, like the 3, 4, 1, 2 at the upper left-hand side. So any one of these they can ask for. Every time they ask, we do another random substitution, and we give them back the answer to that. And each time they ask, it demonstrates a little bit more that we have a solution to the problem. Each answer helps prove that we have a solution. In and of itself, it doesn't prove too much, but over a repeated set, it proves it. So, for the solution of 1, 2, 4, 3, which is the second down row, that's this one right here. Okay, they ask for that. After the substitution, we've got a 4, 3, 2, 1, which demonstrates, because they can add it up and get the same consistent value, that we've given them back a correct answer. So the first question is, was anything given away? Well, that's what the random substitution prevents, is us giving away a piece of our solution. It only demonstrates that we have a solution. And can they ask repeated times? Yep, they can keep asking, and provided we have a solution, we can keep giving them correct answers. So after enough correct answers, the verifier is going to become convinced that, yeah, they have a solution to it. And if the Sudoku is sufficiently large, not our teeny little example, then having gotten a solution is NP complete hard, and being able to demonstrate that is hard. So having a solution, the setup time is hard, but once you have a solution, the answers are easy. So this is your normal interactive solution case for the ZK part in zk-SNARK. But it doesn't give us a problem that is in this category that has a sufficiently unlikely probability. So we have to do it a bunch of times to get that probability. The SNARK part is where we pick a different kind of a problem, also NP complete, but one that has a likelihood distribution that if you give them back an answer, it is sufficiently improbable to give them an answer that could be a lie, that it proves in one pass that you actually have this. So in the land of cryptography, what we're looking for is something that has a range of possible solutions that is really large. And the easiest example of a range of possible solutions that is really large is something like all the polynomial curves in a 2D plane, which we know is a second-order infinite set. So this is not just the number of points in the plane that's countably infinite. This is bigger than that set. So being able to use a curve out of the plane as your thing that you're going to demonstrate that you have means that if we can pick a point on the x-axis and we can produce a correct verifiable result on the y-axis, or vice versa, that combination demonstrates that we have, in fact, that polynomial function. And since it is such a large set, the probability of us being able to fake it is essentially 0. So a single proof of correctness on that demonstrates that we have the 0 knowledge, that we actually have the correct polynomial with the correct values. And the references there is an article on how you turn programs into these kinds of polynomial solutions. If somebody is interested in some kind of field of research, this is probably one of the most important ones that I can think of today, because this is something that has definite applications for security, for blockchains, for provability of all sorts of kinds of things, and it is sufficiently difficult to get your head around in any kind of practical way that once you've developed a solution to it, you're going to be a world expert on this particular thing. So, this has lots of potential. I mean, I can definitely see where somebody could do easily a master's, if not a PhD, coming out of this kind of work.